Hello friends, I am Chandan. Today's topic is heat transfer in flow over plates and pipes. This is important topic which is asked in GATE exam. I will discuss some important question in this topic. So let's start the question. Question number 2, which is very important question. Just read the question carefully. You have to read the question carefully. Okay, so this is the question here. So a fluid flowing over a flat plate has the following properties: dynamic viscosity, that is equal to 25 into 10 to the power minus 6 kg per meter second. Specific heat, that is equal to 2.0 kilojoule per kg Kelvin. Thermal conductivity, that is equal to 0.05 watt per meter Kelvin. The hydrodynamic boundary layer thickness is measured to be 0.5 millimeter. Okay, the thickness of the thermal boundary layer would be, 4 option is given: 0.1 millimeter, 0.5 millimeter, 1.0 millimeter, none of these. Okay, so first of all you have to write which is given in this question. So let's start which is given in this question. Let's write. Okay, question number 2. So a fluid flowing over a flat plate has the following properties: dynamic viscosity mu, that is equal to 25 into 10 to the power minus 6 kg per meter second. Specific heat C, that is equal to 2.0 kilojoule per kg Kelvin. Okay, thermal conductivity K, that is equal to 0.05 watt per meter Kelvin. The hydrodynamic boundary layer thickness, that is equal to 0.5 millimeter. The thickness of the thermal boundary layers would be, so you have to find out what is the thermal boundary layer thickness. What is the thermal boundary layer thickness? Okay, so what is the formula? First of all, we know the formula, that is hydraulic boundary layer thickness by thermal boundary layer thickness, that is equal to Prandtl number to the power 1 by 3. Prandtl number to the power 1 by 3. So first of all you have to determine what is Prandtl number. You have to calculate what is Prandtl number. So Prandtl number, that is equal to mu Cp by K. That is mu. What is the value of mu? That is 25 into 10 to the power minus 6. So this is 25 into 10 to the power minus 6. What is the value of C? That is 2 kilojoule. That means 2 into 1000 by K. K, that is 0.05. If you calculate this value will be 1. Okay, so from here hydraulic boundary layer thickness, that is equal to 0.5, and you have to calculate the thermal boundary layer thickness, that is equal to Prandtl number 1 to the power, Prandtl number which is 1 to the power 1 by 3. From here delta T, that is equal to 0.5 millimeter, because this is millimeter, 0.5 millimeter, so this is equal to 0.5 millimeter, because this is 1, this whole is 1, so delta T, that is equal to 0.5 millimeter. So this is the correct answer. So the correct answer is option B, 0.5 millimeter. Okay. So the next question, which is very very important question, which is question number 6 and 7. Question number 6 and 7. So read the question carefully. First question number 6. Read the question carefully. This question. Read the question carefully. So what is given in this question? So an uninsulated air conditioning duct of rectangular cross section 1 meter into 0.5 meter, carrying air at 20 degrees Celsius with a velocity of 10 meter per second, is exposed to an ambient of 30 degrees Celsius. Neglect the effect of duct construction material for air in the range of 20 to 30 degrees Celsius. Data is as follows: thermal conductivity, that is 0.025 watt per meter Kelvin, viscosity, that is equal to 18 micropascal second, Prandtl number, that is equal to 0.73, and density, that is 1.2 kg per meter cube. For laminar flow, Nusselt number, that is equal to 3.4 for constant wall temperature condition, and for turbulent flow, Nusselt number is 0.023, Reynolds number to the power 0.8, and Prandtl number to the power 0.33. Okay, then the Reynolds number, you have to find out the Reynolds number for the flow. Okay, so write down what is given in this question. Okay, first you have to write what is given in this question. So in this question number 6. So an uninsulated air conditioning duct of rectangular cross section. So this is the rectangular cross section. Okay, rectangular cross section 1 meter into 0.5. So this is 1 meter, this is 1 meter, and this is 0.5 meter. 0.5 meter. Carrying air. So here T, that is equal to 20 degree Celsius temperature. With a velocity is given, that is 10 meter per second, is exposed to an ambient of, so T infinity, ambient temperature, that is 30 degrees Celsius. Neglect the effect of duct construction material for air in the range of 20 to 30 degrees Celsius. Data is as follows: thermal conductivity K, that is equal to 0.025 watt per meter Kelvin. Viscosity mu, that is equal to 18 micropascal second, that is equal to 18 into 10 to the power minus 6 Pascal second. Okay, and Prandtl number, that is equal to 0.73, density rho, that is equal to 1.2 kg per meter cube. For laminar flow, Nusselt number for laminar flow 3.4. This is for laminar flow, and Nusselt number, that is 0.023, Reynolds number to the power 0.8, and Prandtl number to the power 0.33. This is for turbulent flow. This formula is for turbulent flow. So what is given? So the Reynolds number for the flow, you have to find out what is the Reynolds number. So how you calculate what is the Reynolds number? Okay, we know the formula which is Reynolds number that is equal to rho v d by mu. This is the important formula. Reynolds number that is equal to rho v d by mu. Okay, so this rho is a density, v is the velocity, d is the equivalent diameter of duct. What is d? D is the equivalent diameter of duct, and mu that is dynamic viscosity. Okay, mu that is dynamic viscosity which is given. Okay, so what is d? So you have to calculate the Reynolds number. Okay, so first of all you have to calculate what is the equivalent diameter. So d that is the equivalent diameter of duct. Okay, so if you want to find the value of d, then the formula d that is equal to 4 into cross section area by weighted perimeter. Cross section area by weighted perimeter. So this is the duct here. So you have to find what is the cross section area of this duct. This is 1 into 0.5. What is the cross section area? That is equal to 1 into 0.5. So 4 into 1 into 0.5. 1 into 0.5 means cross section area. What is the weighted perimeter? Weighted perimeter means you have to just find out the perimeter. Perimeter that means 2 into this plus this, 1 plus 0.5. So this is 1 plus 0.5. Okay, so from here that is 4 into 1 into 0.5 divided by this is 6. Okay, if you calculate that value, this value will be 0.667 meter. 0.667 meter. So that's just put the value of to calculate the Reynolds number. Okay, so Reynolds number that is equal to rho Vd upon mu. So Reynolds number rho, what is rho? That is 1.2 kg per meter cube. 1.2 into what is the velocity? That is 10 meter per second. 10 meter per second into d equivalent diameter, that is 0.667. 0.667. What is the value of mu? Mu that is equal to 18 into 10 to the power minus 6. 10 to the power minus 6. Okay, so if you calculate this value will be 4.44 into 10 to the power 5. So this is the correct answer. 4.44 into 10 to the power 5. So this is the correct answer. Okay, now this is a linked question. So in this question the Reynolds number, so the Reynolds number for the flow is option C is correct. 4.44 into 10 to the power 5. So option C is correct. Now 6 and 7 are same question. Okay, the heat transfer per meter length of the duct is, you have to find out what is the heat transfer rate per meter length. Next, question number 7, you have to find out heat transfer rate per meter length is equal to what? You have to find out heat transfer rate per meter length is what? Okay, so how you calculate? So this is the duct here. Okay, the inside temperature that is 20 degrees Celsius and outside temperature that is 30 degrees Celsius. Heat is transfer from outside to inside Okay, heat is transferred from outside to inside. The heat transfer mode will be convection heat transfer, and the formula of convection heat transfer, that is equal to Q dot, that is equal to H A delta T. From here, Q dot, that is equal to H A delta T means T infinity minus T infinity minus T infinity minus T. Okay, so now just you have to calculate what is the, you have to calculate Q by L. But first of all, you have to calculate what is the value of H, that is heat transfer, convection heat transfer coefficient. You have to calculate convection heat transfer coefficient. How we calculate the convection heat transfer coefficient? So for finding h, small h, for finding small h, so in the first case, Reynolds number, that is equal to 4.44 into 10 to the power 5. So Reynolds number, that is equal to 4.44 into 10 to the power 5. This is greater than 4000. That's why this flow is turbulent flow. This is the critical Reynolds number. Okay, 4000 is the critical Reynolds number. So this calculated Reynolds number greater than 4000. So this is, that's why this is turbulent flow. Turbulent flow. Okay. We know the formula. Formula is given. If the flow is turbulent flow, then Nusselt number, that is equal to 0.023, Reynolds number to the power 0.8, Prandtl number to the power 0.33. So that means Nusselt number, that is equal to 0.023 into Reynolds number to the power 0.8 and Prandtl number to the power 0.33. Now we know what is the formula of Nusselt number, that is HL by K. HL by K. L means this is the HD by K. This is the equivalent diameter. HD by K, that is equal to 0.023 into Reynolds number to the power 0.8 into Prandtl number to the power 0.33. Just put the value. You have to calculate this H into what is the diameter, equivalent diameter, that is 0.667. What is the value of K? K means 0.025. 0.025. That is equal to 0.023 into Reynolds number, that is equal to 4.44. Reynolds number 4.44 into 10 to the power 5 to the power 0.8. Into Prandtl number, what is the value of Prandtl number? That is 0.73. 0.73 to the power 0.33. Okay. From here, you can get the value of H, that is 25.60 watt per meter square Kelvin. Okay. So this is the value of H. Now you have to calculate Q by L, Q dot by L, heat transfer rate per unit length. Okay. So from here, Q dot, that is equal to H into area. What is the area? Area means surface area. So if you, that this area that is the surface area of heat transfer. Surface area. What is the surface area? That is equal to 2 perimeter of this area into length. Suppose the length of this duct is L. So this is the L. Okay, this is the length of this duct. Okay. So the perimeter, what is the surface area? That is perimeter into length. That is 2 into A plus, so 2 into 1 plus, this is 1 plus 0.5, this is this 1, this is 0.5, this is 1 plus 0.5 into L. So this is 3L. Okay. So area, that is equal to 3L. Okay. 3L. Now that is equal to 3 into L meter square. Okay, 3L into T infinity minus T. From here, Q dot by L, that is equal to H. What is the value of H? That is 25.60. 25.60 into 3 into T infinity, that is 30, minus T, that is 20. If you calculate that value, this value will be 768.18 watt, that is approximately equal to 769 watt. So now check the answer. So in question number 7, A, that is 3.8, B 5.3, C 89, and D 769. So 769 is the correct answer. So actually we are getting the value of 768.18, but the option is given, that is 769. So the correct option is 769 watt. Okay, very important question. Just you have to remember this question. Okay, you have to remember that concept. Okay, now the next question, that is also very important. Just read the question carefully. Question number 8. Question number 8. Question number 8. So what is? Just read the question carefully. So in that question, what is given? The temperature distribution within the thermal boundary layer over a heated isothermal flat plate is given by T minus TW by T infinity minus TW, that is equal to 3 by 2 y by delta T minus 1 by 2 y by delta T to the power whole cube, where TW and T infinity are the temperature of plate and free stream respectively, and y is the normal distance measured from the plate. The local Nusselt number based on the thermal boundary layer thickness delta T is given by. You have to calculate what is the Nusselt number based on thermal boundary layer thickness. Based on thermal boundary layer thickness, you have to calculate this Nusselt number. Okay, so first of all, what is given in this question? So question number 8. What is given? That is temperature distribution is given, T minus TW by T infinity minus TW, that is equal to 3 by 2 y by delta T minus 1 by 2 y by delta T to the power whole cube. Okay, to the power whole cube. So first of all, you have to calculate Nusselt number. You have to calculate Nusselt number. So how you calculate this Nusselt number? So Nusselt number in terms of thermal boundary layer thickness, Nusselt number that is equal to Hx delta T upon Kf. Hx means convection heat transfer coefficient at location x, delta T means thermal boundary layer thickness, and Kf, that is conduction heat transfer coefficient. Kf, that is conduction heat transfer coefficient. Okay, so first of all you have to calculate the value Hx. Okay, so what is the value of Hx? The formula, you have to remember this formula, Hx, that is equal to minus Kf dt by dy at y, that is equal to 0, Ts minus T infinity. Ts minus T infinity. This is the formula of Hx. Heat transfer coefficient at location x. Okay, this is the formula. Okay, now from here you can get that is T minus Tw, that is equal to T infinity minus Tw into 3 by 2 y by delta t minus 1 by 2 y by delta t to the power whole cube, bracket close. From here you can get, if it both side you can you have to derivative with respect to y. So dt by dy, that is equal to, so this is common, T infinity minus Tw into 3 by 2 delta t minus 1 by 2 into 3 y square by delta t whole cube. Okay, if this y, if the y, this value is 0, suppose y value that is equal to 0, then you have to calculate this y value is equal to 0. So this is cancel out. Okay, so now you can calculate that dty dy at y equal to 0, that is equal to T infinity minus Tw into 3 by 2 into delta t, that is equal to 3 minus 3 into Tw minus T infinity by 2 delta t. Okay, so what is the formula of Hx? Now you have to find out what is the formula. You have to find out the value of Hx. Hx, that is equal to minus kf into dt by dy at y equal to 0 by Ts minus T infinity. Ts minus T infinity. Okay, Ts minus T infinity. Okay, from here minus kf, you have to put the value of dt by dy at y equal to 0. You have to put this value. Okay, this value. So dt by dy at y equal to 0. So that is equal to minus 3 into T1 minus T infinity by Ts minus T infinity into 2 delta t. So T1 and Ts, this is same. T1 and Ts is same. Okay, so from here you can cut this portion. So from here Hx, that is equal to 3 kf by 2 delta t. From here you can you know that Nusselt number, that is equal to Hx delta t by kf, Hx delta t by kf. So from here Nusselt number Hx into delta t by kf, that is equal to 3 by 2, that is 1.5. From here Nusselt number, that is equal to 1.5. So this is the correct answer. So from here this Nusselt number, that is equal to 1.5. Okay, this Nusselt number, that is equal to 1.5. So check the answer. So in that question, option B 1.50, this is the correct answer. So option B is the correct answer. Okay, next question, question number 9. Question number 9. Okay, read the question carefully. Question number 9. This question. You have to read the question carefully. So in that question, what is given? For flow of fluid over a heated plate, the flowing fluid properties are known. Viscosity, that is 0.001 Pascal second. Specific heat at constant pressure, that is equal to 1 kilojoule per kg Kelvin. Thermal conductivity, that is watt per meter Kelvin. And what is given? The hydrodynamic boundary layer thickness at a specific location on the plate is 1 millimeter. The thermal boundary layer thickness at the same location is. So you have to calculate the thermal boundary layer thickness. You have to calculate thermal boundary layer thickness at the same location. So first of all, what is given in this question? What is given? So write down what is given in this question. So question number 9. So for flow of fluid over a heated plate, the following fluid properties are known. Viscosity, mu is given, mu that is equal to 0.001 Pascal second, and specific heat at constant pressure, that is to 1 kilojoule per kg Kelvin, and thermal conductivity K, that is to 1 watt per meter Kelvin. Okay, 1 watt per meter Kelvin. So hydrodynamic boundary layer thickness, that is equal to 1 millimeter. Okay, so the thermal boundary, you have to calculate thermal boundary layer thickness. So thermal boundary layer thickness is equal to what? So you know that formula. What is the formula? What is the relation between delta hydraulic boundary layer thickness and thermal boundary layer thickness and Prandtl number? What is the formula? That is hydrodynamic boundary layer thickness by thermal boundary layer thickness, that is equal to Prandtl number to the power 1 by 3. From here, hydraulic boundary layer thickness, that is 1 millimeter, and thermal boundary layer thickness, that is you have to calculate this thermal boundary thickness, and Prandtl number, that is mu Cp by K. What is the Prandtl number? That is mu Cp by K. What is the mu? Mu means 0.001. What is the value of Cp? That is 1 kilo. That means 1 into 1000 kilo. That's why you multiplied by 1000. Okay, by K. K means 1. If you to the power 1 by 3. From here you can get delta T, that is 1 millimeter. So this is the correct answer. So delta T, that is equal to 1 millimeter. So the correct option is option C, 1 millimeter. Okay. Now next question number 10. Question number 10. Read the question carefully. Question number 10. So question number 10, read the question carefully. So what is given in this question? So the ratios of the laminar hydrodynamic boundary layer thickness to thermal boundary layer thickness of flow of two fluid P and Q on a flat plate are 1 by 2 and 2 respectively. The Reynolds number based on the plate length for both the flows is 10 to the power 4. The Prandtl and Nusselt number for P are 1 by 8 and 35 respectively. The Prandtl and Nusselt number for Q are respectively. What is the value? That is 4 option is given. Option A, B, C and D. So what is the correct answer? Okay. So first of all, you have to write what is given in this question. Question number 10. Question number 10. So there is a two fluid given, that is the ratio of boundary layer thickness to thermal boundary layer thickness of flows over of two fluids. There is a two fluids, fluids P for fluid P for fluid Q. Okay. So what is given? Now hydrodynamic boundary layer thickness, ratio of hydrodynamic boundary layer thickness to thermal boundary layer thickness for P. So hydrodynamic boundary layer thickness by thermal boundary layer thickness for P, that is equal to 1 by 2, and for Q, hydraulic boundary layer thickness and thermal boundary layer thickness, that is equal to 2, that is equal to 2. Then the Reynolds number based on the plate length for both the flows. So Reynolds number for P, that is equal to 10 to the power 4, and Reynolds number for Q, that is equal to 10 to the power 4. Okay. Now the Prandtl number and Nusselt number for P. Prandtl number for P, that is equal to 1 by 8, and Nusselt number for P, that is equal to 35. Nusselt number for P, that is equal to 35 respectively. The Prandtl number and Nusselt number for Q. You have to calculate Prandtl number for Q, that is equal to what, and Nusselt number for Q, that is equal to what. You have to calculate this value. Okay, how you calculate this value? So first of all, what is the relation between Prandtl number, hydraulic boundary layer thickness and thermal boundary layer thickness? That is Prandtl number, that is equal to hydraulic by thermal to the power 3. Okay, hydraulic by thermal to the power 3. Prandtl number, you have to calculate Prandtl number for Q, that is hydraulic by thermal of Q to the power 3. So hydraulic by thermal, that is hydraulic by thermal for Q, that is equal to 2, that is 2 to the power cube, that is equal to 8. So this is the answer, one answer. So the Prandtl number for Q, that is equal to 8. Now you have to calculate the Nusselt number. You have to calculate the Nusselt number for Q. You know that the formula of Nusselt number, that is equal to 0.664 Reynolds number to the power 0.5 and Prandtl number to the power 0.33. You know this formula. This is very, very important formula. Nusselt number, that is equal to 0.664 Reynolds number to the power 0.5 and Prandtl number to the power 0.33. From here you can write this formula, Nusselt number of Q by Nusselt number of P, that is equal to 0.664 into Reynolds number of Q to the power 0.5, Prandtl number of Q to the power 0.33 by 0.664 into Reynolds number to the power 0.5 into Prandtl number of P to the power 0.33. Now you have to calculate the Nusselt number for Q. So Nusselt number for Q, you have to calculate. The Nusselt number for P, that is 35. 35 is given, that is equal to this cancel out here, and Reynolds number is cancel out because Reynolds number is same for both the fluid. So 10 to the power 4 and this is the 10 to the power 4. Okay, so Prandtl number of Q, that is 8 to the power 0.33 divided by Prandtl number of P, 1 by 8 to the power 0.33. From here Nusselt number of Q, that is equal to 140. So Prandtl number 8 and Nusselt number 140. So here the correct option is option A, Prandtl number 8 and Nusselt number 140 for Q. Q fluid. Okay, so option A is the correct answer. Okay, now last question, that is question number 13. Question number 13. So read the question carefully. Read the question carefully. Question number 13. So what is given? Water flows through a tube of diameter 25 millimeter at an average velocity of 1 meter per second, 1.0 meter per second. The properties of water are density, that is rho, equal to 1000 kg per meter cube, mu, that is equal to 7.25 into 10 to the power minus 4 Newton second per meter square, k, that is equal to 0.625 watt per meter Kelvin, Prandtl number, that is 4.85. Using formula is given, Nusselt number 0.023, Reynolds number to the power 0.8, Prandtl number to the power 0.4. The formula, that is very important. This formula is given. The convective heat transfer coefficient. You have to calculate what is the convective heat transfer coefficient. So first of all, you have to write what is given in this question. Okay, so this is question number 13. Question number 13. What is given? Water flows through a tube of diameter. Diameter of the tube is given. Diameter of tube, that is 25 millimeter. At an average velocity. Velocity is given, that is v equal to 1.0 meter per second. The properties of water density is given. Density rho, that is equal to 1000 kg per meter cube. Mu, that is equal to 7.25 into 10 to the power minus 4 Newton second per meter square. K is given. K, that is equal to 0.625 watt per meter Kelvin. Prandtl number, that is equal to 4.85. The formula, Nusselt number formula is given, that is Nusselt number formula, that is 0.023 into Reynolds number to the power 0.8 and Prandtl number to the power 0.4. You have to calculate the convective heat transfer coefficient in watt per meter square Kelvin H. So you have to calculate the convection heat transfer H, small h. You have to calculate the convection heat transfer coefficient. Okay. So the formula is given, that is this Nusselt number. This is the formula is given. So first write on this formula, that is Nusselt number, that is 0.023 into Reynolds number to the power 0.8 and Prandtl number to the power 0.4. From here, what is the value of Nusselt number? That is hd by k. This is the formula of Nusselt number, hd by k. That is equal to 0.023 into Reynolds number, that is rho Vt upon mu to the power 0.8 and Prandtl number to the power 0.4. From here, h, what is the value of d? That is equal to 0.025 meter. 25 millimeter, that is equal to 0.025 meter. So 0.025 by k. What is the value of k? That is 0.625 watt per meter Kelvin. 0.625, that is equal to 0.023 into rho. What is the density? That is 1000 into v, that is 1 into what is the value of d? D means rho Vt. D means this small d. That is 0.025. This is d. Okay, this is d. Okay, so here this is 0.025 by what is the mu? That is 7.25 7.25 into 10 to the power minus 4 into minus 4 to the power 0.8 into what is the Prandtl number, that is 4.85. 4.85 to the power 0.4. From here you can calculate the heat transfer coefficient, convective heat transfer coefficient H, that is equal to 4613.66 watt per meter square Kelvin. So this is the correct answer. So H, that is equal to 4613.66 watt per meter square Kelvin. So this is the numerical answer type question. So 4613.66 watt per meter square Kelvin. So the correct answer is H, that is equal to 4613.66 watt per meter square Kelvin. So that's all in today's topic. So thank you everyone. Thank you.